Hello and Assalamu alaikum. The topic of today's lecture is clippers. By definition, clippers are the networks that employ diode to clip away a portion of an input signal without distorting the remaining part of applied waveform. There are two general categories of clipper circuits. These are series clipper circuit and parallel clipper circuits. The figure A shows an example of series clipper circuit where diode is in series to the load resistor, and in case of parallel clipper circuits, diodes are in parallel to the load. Here load resistor is absent and we consider this open circuit as load. That means we are measuring output at this point, which is parallel to the diode. So let's do an analysis of this simple series circuit. Now we are going to apply an input signal to this circuit and we want to see what will be the output, and output we are going to measure against this resistor R. Here first input signal is a square waveform which have the magnitude of V voltage for the positive half cycle and minus V voltage for the negative half cycle. Now if we apply this input signal at the input side of this series clipper circuit, we will get this output signal. We are going to apply this circuit. We are going to apply this input signal to this circuit in parts. That means we are going to apply first the positive half cycle of this signal and then the negative half cycle of this signal to this circuit. Why we are doing this? Because for the positive half cycle of this signal, the diode is forward bias and it is conducting, and for the negative half cycle of this input signal, diode is reverse bias and it is replaced by an open circuit. So depending upon whether diode is conducting or it is an open circuit, the output is determined. So let's see. First we apply a signal which is from 0 to T by 2, that is plus minus V. So in this case, the diode is conducting and we can replace this diode with an equivalent short circuit. Now we have the simple circuit where we can apply KVL to determine this output voltage. Let's apply KVL. We have a rise of V and no drop against this diode because this is an ideal diode, and then we have a drop of V naught, which is against this resistor. So this means V0 is equal to V. What does this mean? This means whatever the voltage we have at input side will be replicated at output side, and the output signal will be as we had in input waveform, that is the positive half wave. Now if we apply the negative half cycle, that is from T by 2 to T to this circuit, what will be the output? So let us apply the negative half cycle of the input waveform to this circuit. That means we are applying V voltage with this polarity. That means negative side of this input signal is connected here and the positive is at ground. Positive is at ground. In this case, diode is reverse bias. Diode is reverse bias, and we can replace diode with an open circuit. Now if diode is an open circuit, there will be no current flowing through this diode, and of course this is a series circuit, so no current will be flowing through this R as well. So in this case, if there is no current flowing through the R resistor, that means the voltage V0 will be equal to 0. V0 will be equal to 0 volt, which is shown here when the input waveform is in the negative half cycle, the output is 0 volt. Similarly, if you have a triangular wave which have the maximum peak of V voltage, if you apply this signal to this circuit, you will get this output waveform. That means for the positive half cycle, diode is conducting and the input signal will appear against this R resistor. And for the negative half cycle, the diode will be reverse bias and it can be replaced by open circuit. So there is no current flowing through the circuit and the output will be 0 volt. Generally, for the analysis of clipper networks, there is no set procedure, but we have listed down few steps which will be helpful for the analysis of any clipper circuit. These are 4 steps. First one is we have to take care where the output voltage is defined against output voltage is defined in the network. For example, in this case, the output voltage V0 is defined in parallel to this resistor R. The second step is we should make an overall sense that the input signal applied to this network, what does the effect this have? That means the input signal will make this diode either forward bias or reverse bias. In this case, we are applying a sinusoidal wave which is alternating waveform, and for the positive half cycle of this input wave will turn on the diode, meaning the positive half cycle will forward bias the diode and the negative half cycle will try to reverse bias or turn off the diode. Furthermore, we can see a DC voltage source which is connected in this branch. We should make sense of this also. In this case, this DC source is trying to reverse bias the diode. We can see the negative terminal of this DC source is connected to anode of this diode. That means this source is making this diode reverse bias. So this was the second step to analyze these clipper circuits. First step is we should determine the transition voltage. The transition is the point on time actually where diode change state from off to on. For example, for this applied signal, we have to see at what point of positive or negative cycle the diode will be forward biased, or you can say the diode will be turned on. So let's find the transition voltage of this circuit against this applied input waveform. The circuit we have drawn here is called as transition state. Transition state means when diode is on, at that instant the voltage drop against the diode is 0 volt and the current flowing through the diode is also 0 ampere. That means at the instant when diode turned on, there is no current flowing through the diode and of course through the load resistor. In this case, we can say this is a transition state. Transition state means when diode gets on from the off state. So let's see at what point of input waveform these conditions occur, and beyond that diode will be on and below that diode will be off. So let's consider this circuit when diode have a DC voltage source in its branch, and that DC source is trying to make this diode reverse bias. And as we see, when we apply this half waveform, that means from 0 to T by 2 positive half cycle, and this is negative half cycle from T by 2 to T. So when we apply this positive half cycle, this should try to make diode forward bias, but against this pressure the DC voltage source is trying to make this reverse bias. So when the input waveform have higher magnitude than this applied DC source, at that point diode will be forward bias and it will start conducting. So let's see at what point this should start conducting. So this was the transition state we already have drawn here. Now if you want to find the value of voltage when diode will be on against this input signal, we can just apply KVL at this circuit. So let's apply KVL. We have a rise of VI and we have a drop of V volt, and then there is no drop as VD is equal to 0 volt, and there is no drop against this resistor because IR is also 0. So V is equal to IR and we have 0 volt against this R resistor. So we have only one rise and one drop in this whole loop. That means VI which we found is actually instantaneous voltage, which we call transition voltage. So when VI is equal to V, the transition will occur. We can mark this on this waveform plot. VI is equal to V, that is transition point, and when this VI gets larger than this V value, the diode will get forward bias and it will turn on, and when this VI value, the input waveform, gets smaller than this V value, which is DC source, the diode will get reverse bias and it will be off. So transition voltage we found from this condition and just by applying KVL. This is actually transition voltage. Now the fourth step is draw the output waveform directly below the applied voltage using the same scale. This is a very good practice that we should draw the output waveform with the same scale as this input waveform is given, and at the same scale at both axes. So if you want to plot V naught against time t, we should plot it directly below the input waveform, so that we should understand when diode was on what was the output, and when diode was off what is actually the output. So as we knew that this transition voltage or transition state is marked here, and that is equal to V. Below this diode was off, and above this diode is on. So if we start from here, then at time 0 diode is off, because time 0 is here and input waveform is less than this DC source. So diode is off and output voltage is actually 0. So until this point, when input reaches Vi reaches this V voltage, the output is 0, because diode is off. So if diode is off, no current is flowing through the resistor and V naught is equal to 0. As we reach this point, when Vi gets equal to V, diode gets on and current starts flowing. But at this point, current is still 0, so output is still 0. Beyond this, when input voltage gets bigger and bigger, then current will increase and there will be some voltage appearing against this resistor R, that will be V naught. So let's assume we are in this region, that is portion of the positive half cycle. Now diode is on and this is the state of circuit. We can apply a KVL here to find V naught against this input signal and against the effect of this DC source. So rise is Vi, and then we have a drop, and then we have another drop of V naught. So if you write the equation of this KVL, then we will get V naught is equal to Vi minus V. Let's apply this. We have a rise Vi, then a drop of V, and then a drop of V naught. So V naught can simply be written as Vi minus V. So let's assume we have this is, let's say this is 2 volt, peak value is 5 volt, and this is 3 volt for just an example. So for Vi is equal to 3 volt and V is equal to 2 volt, V naught will be equal to 1 volt. 1 volt. So 1 volt. Similarly, when Vi is equal to 5 volt, V naught will be equal to 3 volt, and so on. Just we are putting the values of Vi and V in this equation to find V naught. So as we know, at this falling edge, when Vi becomes V again, this is transition point, the diode will get off again and we will have V naught equal to 0. So at this point V naught becomes 0 again. Beyond this whole region, the full negative half cycle and part of positive half cycle, diode is off and we can say output is 0 volt. And what about this peak value? This is, as we know, Vi becomes Vm at this peak. So this is Vm minus V. Now let's solve the example of this series clipper circuit. We have this circuit with 5 volt DC battery and diode orientation is like this, and we have to apply this sinusoidal waveform which has peak value of 20 volt. So following the steps, if you see, first you have to determine where output is defined. Here output is defined against this R resistor. So we are going to find V naught against this R resistor. Second one is to make sense how this input waveform tries to change the state of diode, and also the DC battery, how it affects the state of diode. In this case, we know the positive half cycle will try to make this diode forward bias, and we know the DC source is also trying to make this forward bias. But for the negative half cycle, when this waveform tries to make this diode reverse bias, in this case, this will oppose the effect of this negative half cycle until this becomes greater in magnitude than the DC source. That means if you apply minus 6 volt, like this is minus 20, and when it is minus 6 volt, that will be greater than positive 5 volt. In that case, this diode will be off and we will have V naught equal to 0. So this was just overall sense of this circuit. The third point was to find the transition voltage. The transition voltage we find by putting this transition state in the circuit. That transition state means diode just gets on from off state, and we have Vd is equal to 0. There is no voltage drop against diode because diode is ideal diode, and at transition point Id is also equal to 0 ampere. So in this case we have this circuit, and if you apply KVL on this circuit, you can find transition voltage, and this is rise Vi, and then we have again a rise of 5 volt, and we don't have any drop. So we don't have any drop. So we can find Vi is equal to minus 5 volt. That means transition voltage is minus 5 volt. What does this mean? This means that diode is on for this whole state and it will become off of reverse bias when you reach the this portion of waveform. So for the first step, which we have to apply that we find output voltage and draw output voltage to the same scale we had the input waveform. So let's find the output voltage. Okay, let's find the output voltage V naught against this input signal to this circuit. So for the positive half cycle, as we know, the diode will be forward bias and it will conduct. And we can easily say that for the whole positive half cycle, diode will conduct because transition voltage is minus 5 volt and here diode is on and we have diode off in this state. So for the Vi, when Vi is equal to 0 volt, that means at the time 0, let's find the value of V naught. V naught is equal to Vi plus 5 volt. How this equation is actually derived, you can see this circuit when diode is conducting and now except the transition point, when Vi increases, the current will increase from 0 ampere. So when current increases, there will be some V naught because now we have current flowing through this resistor R. So let's find V naught in this circuit. We have a rise of Vi, then a rise of 5 volt and then a drop of V naught. So V naught is equal to Vi plus 5 volt. V naught is equal to Vi plus 5 volt. So we are going to find Vi at time 0 when Vi is equal V naught at time 0 when Vi is equal to 0 volt. So putting in this equation, V naught will be equal to 0 volt plus 5 volt. That means we have V naught 5 volt. So we will start our plot from 5 volt. It's above 0. Now you increase Vi, you will get more and more V naught until you reach this peak value. Let's put peak value here. V naught is equal to, the peak value of Vi is equal to 20 and plus 5 and both are in volts. So V naught is equal to 25 volt. So peak value of V naught is equal to 25 volt. Now again on the falling edge, when Vi becomes 0 again, then we have V naught is equal to 5 volt. We have shown from this equation. And further, if you reduce this Vi, let's assume Vi is equal to -1. So putting -1 plus 5 will give you 4 volt, again a positive value, until you reach -5 volt. -5 volt, you put -5 when Vi is equal to -5 and +5, this DC value V0 will be equal to 0 volt. So V0 is 0 for this time, that is beyond T by 2. So V0 becomes 0 for the point where Vi equal to -5. And we know diode is off when Vi is larger in magnitude, a negative value, than this value V, that is 5 volt. So for this case diode is off and there is no current flowing through this circuit, and V0 becomes 0. This whole region diode is off and V0 is 0, but before T, the time period, again Vi becomes larger than -5. That means not in magnitude but -4 volt, let's say. So at that point diode becomes on and we have some positive value of V0 if you put this in this equation. So it would have a better idea to draw the output waveform directly below this input waveform, so that we should know where the time period T is and where T by 2 and where this 0 time is. But what about this part of output waveform? This is just extension of this signal, that diode is still on at this point less than 0. Let's say this is some negative value in time. So diode is on, we should have some positive value of V0. So let's move on to another example, which is example 2. Now we have to apply this input waveform to this series clipper circuit, and which is biased clipper circuit, biased with this 5 volt DC supply. So let's see what will be the output. Generally, application of square waveform is easier than the application of sinusoidal waveform. You will notice that these square waveform have only two levels, that is for positive and for negative. And if you consider 0 as a level, then it has 3 levels. So if you apply this signal to this series clipper circuit, we should determine the output voltage which is appearing against this R resistor. So first step was to actually see where V0 is defined. V0 is defined against this resistor R. The second step was to find to make a sense how this input waveform is affecting the state of diode, either making it forward bias or reverse bias, and also what will be the effect of this DC supply on the state of diode. Now the third step was to find transition voltage, but in this case we know there are only two levels, that is 20 volt and minus 10 volt. So generally in the second step we are actually making sense how this will affect on the state of diode. Let's see, for the positive half cycle, when you apply 20 volt here, that is positive 20, of course this is enhancing, means both DC source and the alternating source both are in the same state, that is applying positive voltage on the terminal anode of diode, so they are making this forward bias. So diode will be on for the whole positive half cycle. And what about negative half cycle? When you apply minus 10 volt here, of course minus 10 is larger in magnitude than 5 volt, so it will uh, uh, have greater effect on this diode, so it will make it reverse bias, negative half cycle. So there is no need to find transition voltage, so we just apply first the positive half cycle and then the negative half cycle to this circuit. For the positive half cycle, that is we have only one level, 20 volt. Let's apply 20 volt and we are showing a DC voltage source here, that is 5 volt, and diode is on. And since this is ideal diode, we are replacing this with a short circuit where VD equal to 0 volt, and there is some current flowing through this diode IT, and that current will flow through R, and which will establish some voltage against this R, and that is V naught. So simple application of KVL will give us an equation through which we can find V naught. So let's apply KVL. We have a rise of 20 volt and then a rise of 5 volt, and then we have a drop of V naught. So V naught is equal to 25 volt. V naught is equal to 25 volt for the whole positive half cycle of input signal. And when input signal becomes negative, that means we should change these terminals, negative, positive, and apply 10 volt here, as the magnitude is minus 10. So in this case diode is off, diode is off, and there is no current flowing through diode and through the resistor, and we have output of 0 volt. So we have drawn the output waveform here. Now the other type of clipper circuit is parallel clippers. We know in parallel clippers we measure output in parallel to diode, or we can say diode is in parallel to the load resistor. Here load resistor is not present, so diode is in parallel to this open circuit where we are measuring output voltage. Here are two actually input signals. We have applied these input signals to this parallel clipper circuit and we found the output. Let's see how we can apply this input signal and get this output. First we apply this square waveform to this parallel clipper circuit and see the condition of diode, whether it's forward bias or reverse bias. So if you remember that application of positive half cycle and application of negative half cycle will have different effect on this diode. So let's consider first we apply positive half cycle, that is 0 to t by 2, and then we will apply negative half cycle. So for the positive half cycle we have the voltage V. Let's apply positive half cycle. That means we are applying this V volts at the input side, and this V volts, application of V volt will make this diode forward bias. When diode is forward bias, and we know this is an ideal diode, the voltage drop against this diode will be equal to 0 volts. So for the application of positive half cycle, the output voltage is 0 volt. And when we apply negative half cycle, that means we apply minus V, here. So this negative terminal is connected to anode of diode, and that will make it reverse bias. That will make the diode reverse bias, and we can replace diode with an open circuit. So in this case, if you apply KVL, we can find what will be V naught. So we can find V naught by just application of KVL. Let's apply KVL. We have a drop of V. We have a drop of V, and then we have a drop of V. V naught. And there is no rise in this whole loop, so we can say 0 volts. So V naught is equal to minus V, that is minus V. Similarly, if you apply this triangular wave to this parallel clipper circuit, we will get this output. For the positive half cycle, diode will be forward bias, and you can replace this with a short circuit, and we know there is no voltage drop against a short circuit, so the output voltage is 0 volt for the whole positive half cycle. And when you apply negative half cycle, the diode will be reverse bias, and we will have V, this triangular waveform like we had in input wave. So this means whatever the input waveform is, that will appear against output for the negative half cycle. Now considering this example, we have a parallel clipper circuit and this input waveform. Let's apply this input waveform and see what will be the output. So the four steps we remember are, the first one is consider where output voltage is defined. We know output voltage is defined against this whole branch, not only against this diode but also including this DC source. So output voltage is defined against this whole branch. Next is make an overall sense. So let's make an overall sense. For the application of positive half cycle, this diode will try to get reverse bias, because when you apply positive here and ground here, diode will be reverse bias. But the application of this DC source will oppose the effect of positive half cycle, because this DC source is trying to make this diode forward bias, because positive terminal is connected to anode of diode. Now we should find the transition voltage for this case, because we don't know where diode will get a reverse bias and at what point diode will get forward bias. So to find transition voltage, we have replaced uh, the diode with a short circuit. And as we know, at the point of transition, when diode just gets on from the off state, current is still 0 ampere. So this is called transition state. Let's apply KVL and we can find transition voltage. So in this circuit, if you apply KVL, and we know the rise of VI and drop here is 0, because current is 0, drop of VR is 0 volt, and then drop against the diode is also 0, because diode is just on, and then we have a drop of 4 volt, which is DC source. So transition voltage is 4 volt. Transition voltage we can mark here is 4 volt. That means when the input waveform gets larger than this 4 volt, that diode will become, in this case diode will become off, because applying greater positive voltage here will make diode off or reverse bias. So in this case diode will be off for larger voltage than 4 volt, and it will be on for lesser voltage than this 4 volt. Now we have marked this transition voltage on this input waveform. We can draw the output and we can do analysis of this circuit. So let's draw the output waveform, or let's find the output waveform against this circuit. Now we know 4 volt is the transition level. So beyond this diode is off, and below this diode is on. So let's apply pointwise this input waveform to this circuit and find the output voltage. This is the right way of plotting the output, that is right below the input waveform with the same scale on both axes. So let's find the output voltage. When input voltage was 0 volt at time 0, what was the output voltage? When input voltage is 0, we can see diode is on and is conducting. We can find the output voltage by applying just KVL. So when we apply positive voltage VI, that is rise, and we have current flowing through this. If you consider applying KVL in this direction, but let's apply KVL in this direction to actually uh, maintain the current in the arrowhead direction of diode. So let's apply KVL in this direction. So we have a rise of 4 volt, then drop of 0 volt against this diode because diode is on, and drop of VR, and then a drop of VI. So this is actually the equation. But as we know, we have V naught right against this branch. So we just consider what will be the voltage at this branch. Now you see the output voltage is right in parallel to this branch. In this branch we have a 4 volt rise and then a short circuit in case of diode conducting. So output should be just 4 volt. Output should be just 4 volt until diode gets off. When the input waveform reaches this 4 volt transition level, diode gets off or reverse bias, and you should replace diode with an open circuit. Now we know if there is an open circuit in whole branch, the whole branch will get open. So in this case, this whole circuit gets open circuit and there is no current flowing. I is equal to 0 ampere in this circuit. In this case, whatever the input voltage will be will appear against the output. So whatever the input voltage is appearing against the output terminal. So the same waveform we can replicate here at the output waveform. But when input waveform reaches again the 4-volt level, the diode will get on and this becomes short circuit again, and we are connecting 4-volt directly to output, and we will have 4-volt at output until diode gets off again. But until T, we should plot the output voltage for the whole cycle. That means from 0 to T, or you can say we should plot a whole time period of an input waveform, output waveform, to actually represent the output voltage. Now, in your book, there are some examples of series and parallel clipper circuits where the input voltage waveform is given, and we have to apply this waveform to these circuits, and we have the output voltage waveform drawn here. We should match the output whether our answer is correct or not. So you have to try it one by one. First, for the series clipper circuit, you should apply this input waveform to this circuit step by step and find the output and match your answer with this given output. Simpler clipper circuit and with the biased clipper circuits also. And we have some positive clipper circuit and negative. Positive clipper means it clips away the portion of positive waveform, and negative clipper circuits mean it clips away the portion of negative waveform. Similarly, we have the examples of parallel clipper circuits where the input voltage input waveform is given. You have to apply this waveform to these circuits and find the output, and then you can match the output with this given output. Okay, that is end of this lecture. Thank you very much.